brains and don't turn them off. Okay, so we want to talk about orienting a surface. You guys have talked about parameterizing surfaces. So a two-dimensional surface takes how many parameters to describe it if you're parameterizing it? How many variables to parameterize a two-dimensional surface? 2. That's what your homework was, right? You were picking the 2 variables that allowed you to represent every point, x, y, z, on the surface. Okay, so let's talk about orienting a surface. So on each point of a surface, there are 2 directions normal to the surface. That should make sense. So if you think of a point, there'd be equal and directions opposite to one another. That would be normal to the surface. And so a surface is orientable if one normal at each point. So please don't sacrifice listening and understanding for writing it all down. So if you can take good abbreviated notes or just listen and do this later when watching the video, but don't write everything down and sacrifice listening and understanding. Okay? A surface is orientable if one normal at each point can be picked in a continuous way, and that is kind of the same as saying the surface has 2 distinct sides. So here's an example. And then the direction of the orientation we're going to call n. So n is a vector, and that's the direction of the orientation. Okay, so here's an example. So this surface, you see that it has 2 sides to it, kind of a top and a bottom in this case, okay? And so I'm picking n to be something like upward, right? N is upward. Could pick n to be all the opposites of those vectors and be downward. Okay, so this is an example of an open surface, all right? An open surface has a boundary C that separates 2 sides. So can you see what the boundary C is? That if you cross it, you go from one side to the other. So that would just be that kind of the loop around it, right? If you cross over C, then you're crossing from either the top to the bottom of it or the bottom to the top. So that's an idea of an open surface. And commonly, positive x, positive y, or positive z are chosen as the orientation. That'd be or, right? Not all 3, just one of those. Okay, so then a closed surface has an inside and an outside. So it's a surface that encloses a 3-dimensional space inside and then all the 3-dimensional space outside. So here's an example of a closed surface. And normally, but it doesn't have to be, you orient it from inside out, the way I'm showing it here. So typically inside pointing out is the orientation, but you can have outside pointing in, and that's perfectly legitimate. Okay, so then what's a non-orientable surface? So these are orientable because they have kind of 2 sides, and if you pick n, say you pick this n here, and then you start continuously, you pick this one, well that means you pick this one, and then this one, and this one. When you do that, you get no ambiguities. Then all the points kind of are on the ends kind of are in the same direction, and that's the same with this closed surface. So what about something that's non-orientable? So it's non-orientable if you start assigning these n vectors, and then it leads to an ambiguity. All right, so you know what a Mobius strip is? So we take a strip of paper, and you put one twist in it, and you connect the ends. Okay, so this is not orientable. It doesn't have 2 sides. It kind of just has one side. So if you imagine, so we start with this one here, right? And so then that would make this one, and then this one, and then this one. Wait a sec. Is that the top? Yeah, okay, sorry. Let's try again. My brain isn't seeing it. Okay, so this one, and then this one. Okay, then this, all right, so it'd be behind there, coming out like that, and then here. Is that right? Do I have it now? Yeah. So you keep going like this. We're like, oh, this is the end side. This is the end side of the surface. And then what happens? We come around here, and we're still on the same side, and then this vector is pointing back here at point P. So you can't orient this because you start assigning the ends, and then you get back to where you started, and then ends pointing the other way. Does that make sense? So there's not two sides to this. So you can't orient something like a Mobius strip. So when all the problems we're going to do, we have to have surfaces that are orientable. And that will be either open surfaces with a boundary C, or closed surfaces. And then what's the boundary of the closed surface? Well, it kind of is the surface itself, right? To get from the inside to the outside, you have to cross through the surface. So yeah, so the boundary for a closed surface is S itself. Okay, any questions on surfaces, orienting surface? Yes, sir?
So the reason that doesn't work is because you don't ever go over to one side. You don't ever switch sides on the Mobius strip.
Yeah, there's only one side. There's no two sides to it, right? If you travel around it, you realize that there's just one side to this thing, and there has to be two sides so that there's like n and then the opposite direction of n. Okay. So does that make sense? Yeah. Okay. Other questions? All right. All right. So we're gonna talk about flux. Flux. That's the topic for today. And so to make it easy to start with, we're gonna do flux through flat surfaces to start with. Okay, and before we talk about flux, we have to talk about what's called an area vector. An area vector. So S stands for a surface. S vector is a area vector. Okay, an area vector, we know vectors have magnitude and direction. The magnitude is the area of whatever surface we're talking about. And then the direction of S is n. So what direction is n again? Or normal to the surface, perpendicular to the surface. So it's this vector that represents its magnitude, represents the area, and the direction is orthogonal to that, whatever that surface is. So example, I got a 5.3 horizontal surface in R3, and we want to orient it upward. What would the S vector be? What would the S vector be? Yeah, okay.
15K?
He wants 15K. Does that have the magnitude of the area of the surface? And does it point orthogonal to the surface? If it's a horizontal surface in R3, 15K. He nailed it, right? 15K. That's what that vector is. Okay, so what is flux? Flux is the rate of flow of our vector field F through some surface S. So to calculate flux, it's going to be some kind of product of the vector field and the area vector. So the question is it dot product or is it cross product? Based on what we know. What is dot product again? Product in as much as same direction, cross product in as much as orthogonal. So what do we want? Do we want dot product or cross product? Most are saying dot, some are saying cross product. So remember S, what's the direction of X? S, the direction of S is normal to the plane, right? So do we want to take the parts of F normal to S to get the flow through S, or do we want to take the part of F orthogonal to S, orthogonal M? So you are advocating for dot or cross? But remember, S is orthogonal to the plane already, right? S is orthogonal to the surface already. So do we want F to be in the direction of the n vector or orthogonal to the n vector? Same direction as n, right? So we want the dot product, right? We want the dot product because we want to take the parts of F orthogonal to the surface or normal to the surface. That's the amount of flow through the surface. If we take the part of F that's what parallel to the surface, there's no flow in that way, right? There's no flow in that direction. So you just got to remember that S, the vector S, like we just said, is already orthogonal to the surface, so we want all the parts of F in the direction of S, so we want dot product. Okay, so this is what flux is, right? This is what flux is. Okay, so flux is positive when the net flow is in the direction of N, and negative when the net flow is in the opposite of N. And so again, we've talked about this idea of net before, right? In some parts of the surface, we could have flow in one direction, and other parts of the surface flow in the other direction. So then the total flux is going to be the net results of the whole thing. We'll see an example of that. Okay, so here's an example. So water flows through at 3 centimeters per second through a circular pipe with a radius of 2 centimeters. Find the flux through an elliptical region that has N angled at theta radians to the flow. So here's a picture. Okay, so which way does N point? Up, down, and to the left or right? Which way does N point? S is this like tilted like ellipse. Like think of this is a pipe, and think of a screen on an angle through there. And we're going to calculate the flux through that screen, which will have an elliptical shape once we cut it off by the pipe. So the direction of N, up or down, and up to the right or down to the left or up, whatever. Up to the right, right? So N is going to be up to the right. And then it forms an angle theta with a flow. So how do we calculate the flux? Nice, right? So it's dot product. Remember, we had a alternate formula for dot product would be the magnitude of F times the magnitude of S, and then cosine theta. So we want the flux through S will be F dot S, and then magnitude of F, magnitude of S, cosine theta. So each one, what's the magnitude of F? That's like our vector field, right? F is our vector field, so what's the magnitude of F? Yeah, it's just the 3, right? So this is a constant vector field, right? So if the flow is 3 centimeters per second, then every single vector is just what, like 3, maybe it's 3j or something like that. So the magnitude of F is just going to be 3. It's 3 everywhere, right? What's the magnitude of S? Well said. Whatever the area of that elliptical region is, right? So the magnitude of S is going to be the area of this. So we can kind of make a right triangle instead of out of sides, out of shapes. So we can make it like a right triangle like this. Where this is the hypotenuse is the area we want. And then this side is, what is that side? That's going to be the area of the circle, which would be pi r squared. So then what is, you do the math here, so this is pi over 2 minus theta here, making this angle what? So thinking of like a little triangle here, this is pi over 2 minus theta, and this is another right triangle, so this one is theta. See that? It's theta. So we've got hypotenuse, and theta is down here, and adjacent. So A equals, or this side would equal A, what? Cosine theta. It'd be hypotenuse times cosine of the angle would give us the area of that circle. So what is the magnitude of S? It's going to be 4 pi over cosine theta. Do you see that? So we got 3 is F. The magnitude of S is the area of that ellipse, which is 4 pi over cosine theta, times cosine theta from the dot product formula gives us 12 pi. centimeter cubed per second. So what is that? So what happens there? What does that tell us about what if it were angled at a steeper angle? If that screen were angled at a much shallower angle like this, what would the flux be? Yeah? Be larger?
Yeah.
But what happened? Look. Right? Did it depend on the angle? Didn't depend on the angle, right? So even if that screen is angled like this, or that screen's up and down, the flux this way is the same. Why? Because we're only taking the part that's normal. And so when you take the part that's normal, and that's going to be kind of compensated by how much area you have, right? So it's always going to be 12, no matter what angle this thing is at. Okay, does the idea make sense of flux, right? So the idea that it's F dot S. We want the part of F normal to the plane. And the vector S is already normal to the surface. So by doing dot product, we're taking all of the component of F that's normal to the surface, and that's going to give us that's the flow through the surface. Any parts of F that's parallel to the surface, we don't care about because there's no flow there, right? Okay, anybody have a question? So that's basics of flux. So let's do an example here. All right, so what's different about this one? It's a little bit different. So can we sketch that? The surface x equals 1, 0, y is 0 to 4, z is 0 to 2. So let's sketch that. We should be able to. So x equals 1. Where's that? Yeah, we're going to have a plane that's parallel to, parallel to your paper, or parallel to the screen out in front at 1, right? And then y from 0 to 4. And then z from 0 to 2. Something like that. Okay, and then we have this vector field, y minus 1, z, 0. So what's different about this in the last example? Yeah, right. So as in different parts of the surface, you have different vectors now, right? That last example was really easy because no matter where you were, you always had the same vector, magnitude 3, in the same direction. So now, as soon as you start moving on this surface, your force changes. So, like we've done a million times in calculus, what are we going to do? We're going to isolate a little point, right? We're going to isolate a little part of the surface. And so before we talked about S, well, now this is a little part, so we want the point area vector, right? So rather than the S vector, which we talked about kind of like a globally for a whole surface, we need to break this up into little point vectors. And so that'll be ds. So what is the magnitude of ds, and what's the direction of ds? So first of all, what's the direction of ds in this case? Okay, so what would that be? So we call that I, right? So that's the direction, and then what's the magnitude of that? So what is it? So what's the magnitude of that? So it's a square. dy dz, right? So the little horizontal dimension is dy, the vertical dimension is dz, and it's in the direction of I. So what do we have? We're going to have dy dz I. Or if we want to write that as a vector, it would be dy dz 0, 0. So that's our area vector for this little piece, a little teeny square of the surface. So then how are we going to get the flux to the surface? Seasoned calculus veterans, how are we going to get, yeah? So F ds. Accumulate, right? We accumulate all the flux at all the points, right? So this is just one particular point that we're showing. Now we need to accumulate up all the flux at all the points on that surface. So that would be integral, double integral from so over R. Okay, so this is R. So now we're ready to write it. So what would it be? Double integral. F is y minus 1 z 0 dot dy dz 0, 0. And then that's going to be again over R. So what are we going to get when we do that dot product? Yep, just y minus 1 dy dz. Y goes from 0 to 4 and 0 to 2. So before we find that value, that integral, so that's going to be, that's the flux through S. Accumulating all these little f dot ds's, right? All these little f dot ds's for that whole rectangle. So let's take a look at this, what's going on here. So here it is. So here's our plane living in this vector field, okay? This is the vector field, what we say, y minus 1 z 0. Okay, so in terms of flux then, which vectors do we care about if we want the flux through the surface? Yeah, so you may think the ones around it, but really when it comes down, it's just the vectors that are associated with points on that surface only. So all these vectors that are away from the surface or even close to the surface don't really matter. What matters is the vectors that are actually on the surface. Okay, so here's a sample of vectors that are associated with actual points on the surface. Okay, so you see over here on the kind of where y has lower values, the field is what, pointing in the negative x direction, but then as y increases, the field is pointing in the more positive. So what would you guess for the flux or the net flow through this? Positive. We define positive as positive I. So there's much more flow we see on the right side of this thing coming out at us than what's going back. But now, more than that, we care about these vectors, but then what about these vectors do we care about only to get the flux? As much as it's orthogonal. So we care about those vectors, but then what we really care about is, yeah, so in this case, the x component of those vectors. So do you see the difference between blue and red? Yeah, so all we care about is the blue components of these red vectors in terms of the contribution to the flux. So that's what we want. So that's what when we're doing this, problem, we're we're isolating the vectors associated with the surface only, and then more than that, we're isolating the part of those vectors orthogonal to the surface. Oh, this is so much better than you think. All right, so, and then this confirm that we think it's going to be positive? Yeah, you can have a little negative contribution over here where y is smaller, but lots of positive contribution where y is larger. So that's what you're accumulating when you do that integral. You're accumulating the net flow through this surface of those vectors. Anyone do it? 8. I think that's right. Someone else? Yeah, that sounds right. Okay, questions on that? Okay, so we did that one. All right, oops. So now it gets good. What about flux through any surface then? Flux through any surface. So you guys learned how to parameterize surfaces, right? So generically, the two parameters that you pick are u and v. Please.
I was just wondering if our answer would change if we had like s point the other way, or do we always just?
Okay, yeah. So if we made n, so n, n for s would point in the negative x direction, then what would the answer be? It'd just be -8 because you'd have everything be opposite, right? That small contribution now would be a positive contribution, and then all that stuff on the right side of the plane would be negative relative to our orientation. So we just get -8. Yeah. Okay, so u and v are just generic. So lots of times we use x and y. Sometimes we use r and theta. In spherical coordinates, we might use phi and theta. So u and v is just generic. So I have this generic surface. And again, we've got to break it up into little pieces because, first of all, now the surface is curved, right? So the direction of n is going to change as you move along the surface. And we could be in a vector field that's not constant. So we absolutely have to do this a little piece at a time, right? So we got to parameterize surface r, u, and v. And so then we think about the partial derivatives are going to be really important here. So the partial derivative with respect to u is you hold v constant, right? And then you're actually then, do you remember what the first derivative of a vector function was? Remember our vector functions, if there were curves in space, pointed in the direction of the curve, right? It was like tangent to the curve, pointing in the direction of the curve. And its magnitude was like the rate of change along that curve. So if you change t a little bit, how much of the curve gets swept out. Okay, so we're going to have two of those. So the partial of u with respect to partial of r with respect to u is going to be holding v constant and going along a contour in the u direction. And then partial of r with respect to v is going to be holding u constant and looking at it along the contour in the v direction. All right, so we may get for u, so for r sub u, we may get something like this. Holding v constant, you get this contour, and then you're going to have this tangential vector, and then rv maybe that's like super short like this. Now, what we need to do, though, is we need to scale those vectors so that they approximate the little piece that we want, right? So like I showed that, so that over on the left there, that RU, the length of that vector may, maybe way too long compared to the little rectangular little parallelogram piece that we have, and RV may be way too short. So we need to rescale those so that those two vectors are kind of like approximating the size of our little element. Does that make sense? So we can just rescale those by, so I'm going to put du here. I'll rewrite this, it's blurry. So du ruv. Okay, so by multiplying by du, it will give us the it'll kind of try to approximate, now the length will kind of approximate the length of that side. And then likewise, dv. But now, so there's like the blue element, the actual curved element. And so then that du, ru, and the dv, rv vectors, those will make a plane, right? So we want, that's the pink thing. The pink thing is like a planar version of the blue curved element. So what's the shape of that? What's the shape of the pink flat element that's trying to be like the blue curved element? Getting closer? It's not necessarily, they're not necessarily at right angles, right? These contours aren't necessarily at right angles to one another. So we get a parallelogram, right? These little elements that we're going to use to approximate the surface are like parallelograms. Okay? How do we find the area of a parallelogram? Who remembers? Yeah? In vector calculus, how do we find the area of a parallelogram? Remember this cross product was like week 1, right? Week 1. Okay? So here's our little pink element trying to approximate the blue one. And so to get the area of that red parallelogram, we're going to use the cross product of our two vectors. So the area of the red parallelogram is going to be just do one thing at a time here. So just look at the very far left. It's going to be the cross product of du ru and dv rv. Okay, it's going to give us the area of that thing. And then the du and dv are just constants, so they can come out. You could, if you do the cross product, it's the same as if you pull those out. And so what is that? That's our area, so that's our ds. This is not the point area vector. Don't worry about this yet. We need to talk before we get too far. Okay, so what's the difference between ds and this ds? The first one is just area. It's just the area of your little piece. Now this one has, it's the area along with what? The direction orthogonal to the little piece, right? Okay, so we're going to do, if we do ru cross rv and then times du dv, we'll get the area of that red parallelogram. And that's like the area of our little piece. So kind of, as a side note then, what we've really just discovered is now we can figure out, we can use these flux integrals, but it's not really flux anymore, just to find the area of a surface, right? Because if we do the double integral of ds instead of the f dot ds, then that'll just give us surface area. So this is kind of a nice like little side tangent here. We're working on flux, but what we discover is that we've got surface area. If we just integrate that thing, the area, if we integrate all the area of these parallelograms as things get small, that will be surface area of our surface. So little what do they call that? You take a little side trip on our vacation here to find out that we know we can do surface area with this. What we're really after was flux, right? What we're really after was flux. So what is flux? Flux is going to be has to do with our point area vector, right? So our point area vector is just going to be that n. If you take it one step at a time, it's not so overwhelming, right? So what's our point area vector? That's just the n vector times ds. So where's the n vector going to come from, right? So how are we going to get the vector orthogonal So we want n, right? So we want the unit vector that's orthogonal to our little planar element there. So someone said? Cross product of? Yep. So we do cross product of, so that n will be the cross product of RU cross RV, but then we want to force the area to be ds, so we need this to be normal, unitized, right? So what will we do? Oh, sorry, I shouldn't have put the magnitude on the top. Got ahead of myself. So the top is the vector, right? We want the vector, the cross product, not the magnitude of it. And then we want to divide by the magnitude to get it to be a unit vector. So that's n. So we're going to take that n, and we're going to multiply it by the ds that we already have. And what's going to happen? Do you see what's going to happen? Yeah, but what algebraically? So I'm going to do that times. Magnitudes are going to go away, right? Because I got the magnitude on the bottom in my n vector, and then part of ds, it's on the top. So n times that, right? N, this is our ds. So we do that times that. We're just going to go at the cross product, du dv. And then the flux, well, so this is the point area vector right now. Okay, so yeah, so the point area vector is, everyone got the red stuff? Can I take it off? So then the point area vector is going to be the cross product, the actual vector, times dA, which is the same as du dv. And so then we can write the flux integral. We know what f is, it's just f. So we have some vector field f, and now we have ds, and so the flux will be f dot ds vector, right? F dot ds vector. Did you catch all that? So if you followed along moment by moment, that's awesome. But then you gotta go back and review this because there's lots going on here. And we need to know them. I've tried to really lay this out so it's really focused on the meanings of everything. Okay, I'm trying to inject lots of phrases there so you make sure we keep the meanings of things. So this is a good slide to go back and review lots of times. Anybody have a question? Okay. So let's do an example. So now we've got what? We've got a curved surface and we've got a varying vector field. Now we've got all the as general as we can, right? We're making this as general as we can. So we're going to find the flux through S, which is the part of this paraboloid that lies above the unit square in the xy plane. Oh, so, okay, yeah, it's fine. What's the unit square in the xy plane? Right, so it's going to have its lower left corner, lower left in the origin. It's going to be a square like this. That square I've drawn all day. All right, so, and then we're going to have this paraboloid. And what do you know about that paraboloid? How can you describe it? Opens down from 4. Right, it's going to be circular paraboloid, opening downward, starting at z equals 4. But we just want the part that lies over the unit square. So it's gonna. So what will it do? This will be lower down. Do something crazy like this. this, right? So now, you should be thinking to yourself, when I parameterize this, we're going to have to parameterize this because we need R, right? We need this R UV, right? We need the surface as a vector function, right? What you've been working on in your homework. So what are we going to choose for parameters here? I've got a paraboloid over the unit square. We've got choices. So what's going to be our best choice for parameterizing this? He wants x and y. What's the other possibility? Yeah, not spherical, like polar or cylindrical, right? Polar cylindrical. So because this thing is circular relative to the xy plane, we could think about r and theta, but y is one choice better than another. So y, x or y, x and y, or y, r, and theta. Yeah. Okay, so that's true, but we know we can rewrite. I mean, once we know what x, y, and z are, we can rewrite those in terms of polar. So that's okay. That doesn't bother us. Yeah. Yeah. So the question is, so we can do x and y, or because this is a paraboloid, we could do r and theta. The question is, which is better in this situation? That's the question. Which is better in this situation? Yeah, Charlie. Yep, if we use polar, then we'll get 4 minus r squared. That's true. But think all the way through this problem. What are we going to end up doing in the end? We're going to be doing a double integral, right? What's that? Why? This is all about the unit square, right? The unit square will be a bear in polar coordinates. X equals 1 and y equals 1 are not nice functions in polar coordinates. But so we definitely want to use x and y coordinates here because when we get to the integral, we'll have the easiest possible limits of integration that we could have, 0 to 1, 0 to 1. Okay? So what will it be in xy? X. Yep. You guys are all experts at that, right? Okay, and then what do we need to do? So we want to find the flux. So how are we going to find the flux? Got our F. So we can let's rewrite F then. We can rewrite F here. F will become what? XY still, and then y times 4 minus x squared minus y squared, and x times 4 minus y, 4 minus x squared minus y squared. Okay, got that. So our flux is we just found that it's the dot product of F and ds, and ds is Ru. So in this case, it'd be Rx cross Ry, and then dA, which would be dx dy. So we got to get Rx cross Ry. What is Rx again? The partial of our function with respect to x. So when we do our cross product, remember we do our cross product of vectors, we're going to do I, j, Okay, and then the partial with respect to x will be 1, 0, 2x, or 2x, and then our r with respect to y will be 0, 1, 2y. Do the cross product. So it looks like we'll get, so let's just write this as we go here. So we have the double integral of xy, y times 4 minus x squared minus y squared. Sorry, y, not 4. X times 4 minus x squared minus y squared. Dot. So the I component will be, looks like positive 2x. Everyone see that? Y component, 0 and positive 2y. Z component, 1 minus 0 is 1. That'll be dx dy. Everyone see where I got the cross product of x and y? Now, we never talked about the orientation of the surface. So, but by what we just did, we've decided already. We just didn't talk about it. What is the orientation of the surface? Positive z direction. And why is it according to the way we set it up there? Why is what we've done set that in the positive z direction?
Because the Rx and Ry are just coming straight off from the top point.
Okay. So like, so we've oriented it that way, but we never consciously oriented that way. How did it turn out that we oriented it that way? Not about the partial derivatives. Oh, yeah, it's kind of about the partial derivatives, but so why? What is it about the partial derivatives that has oriented it this way, up z direction? Yeah. So the cross product, right? Cross product defines a direction, right? If we do x cross y, then x cross y, right-hand rule, will be up. So the fact that we did x cross y set the orientation as up by the right-hand rule. Okay, so let's just write out, and then we know this from 0 to 1, 0 to 1. Let's just write out the dot product and stop. So what will it be? 2x squared y, is that right? Plus 2y squared times 4 minus x squared minus y squared plus x times 4 minus x squared minus y squared. Did I do the dot product right? Agree? And then we would do that from 0 to 1 and 0 to 1. And that's just a lot of easy algebra. Right? Just polynomial, antiderivative, evaluating the limits. Questions on this example? What does that give? That gives the flux, which is kind of the net flow through that surface where positive is oriented upward, given that the vector field is x, y, y, z, z, x. So you can think of it like a membrane or a screen, like in a fluid field or a wind field or something like this. And so we're calculating the net flow of the fluid or the wind, whatever, at along the screen for the kind of accumulating it for the whole screen. What's that?
It's like the force pushing against, in the direction pushing against the
If it were a force, yeah. So I was saying it was like flow. It was, if it's force, then it would be like, yeah, it would be the. Let's see, if that were a force field. Yeah, so if it were a pressure field, right? If it were force per unit area, then times areas would give you net force along the whole thing. Yeah. If it were a pressure field, you would be, the flux would be the accumulated force on the whole thing. Okay. Any questions? All right. So lots of our surfaces will be use x and y. So let's generically kind of find out what in general it will be if we have a surface parameterized in terms of x and y. Then let's look at that general case and see what happens. Okay, look at that general case and see what happens, particularly when the parameters are x and y in our surface, because that's a common thing. So then we could define that r is x, y, and then whatever z is some function of x and y. And we have our generic field p, q, and r. And remember that p, q, and r are each functions of x, y, and z. And so what will this be if we just have the generic version of the surface, and we have a generic version of the vector field? Then what does our flux double integral turn out to be? Well, what we need to do, in this case, we need to do Rx cross Ry, right? Okay, and then we know F is P, Q, and R. And then we're going to do the dot product. And we know this is dx, dy. And so then we're going to do all that math and get the most simplified form that we can. I think this is a good thing for you guys to work on. Give this a shot here. So for just the generic version of a surface parameterized in x and y, what does the flux integral turn out to be? So I think we can hammer this out in about 5 minutes. Go for it. Oh, just that. Yeah, that's the right idea. Yeah, yeah. Yep, that looks good. Is this what you got? Okay, so remember these are two different r's, right? This is the z component of the vector field. This is the region. This is the region r that we're integrating over. Okay, so now I want you to look at the last example that we did. What was our R was x, y, and 4 minus x squared minus y squared. And F was no, so just yeah, was it YZ? Is that right? Okay, so now we can, so now that we have this general form, we could just go right to this. We know that we're parameterizing in x and y. We want the flux through our surface, flux of that. So if we were to just write this down, what would it be? Negative p is what? What's negative p? Negative xy times partial of this thing with respect to x is negative 2x, right? Minus q is yz. Y would have to write z out. I won't do it again. And then times the partial of g with respect to y. And then plus r. And r is that thing. Is that the same thing we got when we did it the first time? Should be exactly the same thing we did. So this previous example. Using the formula, instead of starting from scratch, go back to the previous example and apply what we just learned. That if your surface is parameterized in x and y, you can just write down this instead of doing all the cross product and the dot product.
Did you forget an x and y?
Probably. Oh, right. R is x times z, so it'd be this times x. And then now is it the same? So x times z. Okay, so if you want the flux and you have the your surface parameterized as x and y, this is an alternate kind of fast track, right? It's kind of a fast track for the flux. We kind of did the heavy lifting and can just now plug into that. Never losing sight of the meanings on what's going on, right? Questions about that?
That's only for x and y, though, right?
Only if you parameterize in x and y. Now, so if you parameterize, say, in y and z, you could figure out how this would be all be shifted, right? So if it was y and z, so it would probably take you a little bit, but yeah. So we, if we're y and z, we could go ahead and do the same thing and find a similar type formula. But most of the time, the most common one is when we parameterize in x and y. So that's why we derive this one. But if it's y and z, just do it from scratch, right? Go back, find your flux from scratch. Okay, so contemplating. Should we do a closed surface or should we do a polar one? I think we should do a closed surface. So here's what's going on today with recitation. Key is gone. I'm sitting in for Key. And then we're just going to keep going on this. We're just going to keep doing more examples. Anyone can come who wants to come because there's no Thursday recitation, obviously. We got a holiday. So come one, come all, okay? So today's recitation, we'll just keep working on these flux examples, and we might talk about the next thing too, okay? So let's do a closed surface then. Let's do a closed surface example. And we'll do in recitation, we'll try to get to a polar one, like a cylindrical one, and a spherical one too. All right, so we got a closed surface. We want to find the flux through the closed surface that is part of the unit cube below y plus z equals 1. And here's our vector field. let's see if you can first draw that. Can you draw the surface that's part of the unit cube below y plus z equals 1? Okay, you got know what this looks like? This closed surface looks like? Can you be more specific? Yeah, so the bottom is, what's the bottom of it? Square is the bottom, right? And then we imagine the unit cube. What? The unit cube is going to be the cube of side length 1. But then we're going to take y plus equals 1 and shear this thing and just take what's below. So, should have, the left side is a full square, right? And then just cut it right down like that. Did you get that? Some people are nodding. Good, okay? So, how are we going to find the flux through that closed surface? What is it going to mean to find the flux through that? So this is an enclosed surface, right? So normally, we'll have our orientation be from inside out. How will we find the flux? So he's saying we need multiple double integrals because these surfaces are, it's like a piecewise surface, right? It's a surface made up of many pieces. But here's the good news. Rather than, so what did we do when we do RU cross RV? That's like our n, right? That's finding the n. It's finding like a variable n, right? Depending on what the coordinates are, right? So on a curved surface, your n is going to change as soon as you move. Well, the good news here is on any one of those pieces, what? N is just constant. So we don't have to do the cross product for every one. We can just call out what n is. For instance, on this front surface, what will n be? So we'll call n would just be I, right? Well, that's nice. We don't. So this is going to go a lot faster than doing a cross product for each one of these. So that front surface, call it S1, n is going to just be I. Okay, what about this over here on the left side? Negative J. So we'll call that S2 back there, or over there on the left. And then that n for S2, N2 will be negative J. What about the back? Call that S3 back there. Negative I, right? Okay, and then 4 would be the bottom of it, negative K. So that's the bottom is S4. And we got one more to go. It's still a constant, even though it's slanted, it's still a constant. So we can just, we know it's what, at an angle of pi over 4. It's constant everywhere, so we can kind of write this down. So for this surface here, the direction of it will be J plus K, right? And then we need that, so J plus K, or 0, 1, 1, right? But then we need to make that unitized, right? Yeah, divide by the magnitude, which is just square root of 2. So that'll be 0 radical 2 over 2, or 1 over radical 2, or radical 2 over 2, same thing. Something like that. And now from each one of those, f is easy, right? F is just x, y squared, z. But for instance, S1. So now we're going to parameterize S1. Let's just do that one. We're going to get lots of these are going to be really easy because of the nature of the planes. S1 is going to be R1, but we're parameterizing it, right? So say in terms of, so what are our two parameters going to be for R1? So we need two variables that will get us all the points on this front surface. What two variables will those be? Y and Z, right? And that will be parameterized as what? It's always, X is always 1, and then Y and Z. So we'll use that then plugged into our, so then F for that will be XY will be Y. Y squared will be Y squared. And Z will be Z. And it will be dot N. What was our N? 1, 0, 0. So all we get is Y for that front face. So we'll have the double integral of Y dy dz. And then we have a double integral, and the projection into the YZ plane will be this triangle. Right? So Y will go from 0 to 1 minus Z. And Z goes from 0 to 1. So that would be the flux for the front triangle. Do you follow that, everything? So because we've got flat surfaces and they're easy flat surfaces, we don't have to find that cross product. We just call out what N is. It's the same for the whole front surface. That's just I, or 1, 0, 0. Dot product with F, according to our parameterization, 1YZ, and we just get Y. So then that front, the flux for that front will be that. Okay, to be continued in recitation, and we'll do more examples. Yeah, agreeing with each other? Any part of it you want me to talk about? So what did you say for the S2? What variables you use for S2? X and Z. Is it right? Is it right? X and Z? Yeah. X and Z. And then that becomes, what is that? How do we parameterize that? X negative 1Z. Y is negative 1. Well, can't be both. Is it X negative 1Z or X 0Z? Yeah, the Y. So we're talking about the coordinates of all the points on that surface. That's what we're doing when we when we parameterize a surface. We're saying we need all ordered triples on that surface. It's not about the direction N. So what are all ordered triples? There's an X coordinate. Y coordinate is 0, and then Z. Yeah, so I think maybe the negative 1 came from confusing it with N. Is that right? Yeah, so no, this is parameterizing the surface, meaning finding all ordered triples on all points on that surface written in two variables. So nothing to do with N there. Okay, and then what about R3? That's the back. Y and Z. Surface is 0, Y, Z. Make sense? R4 was the bottom. X and Y. So it's what? X, Y, 0. And then R5. So when you got two variables to write all ordered triples on that plane, what variables do we want to write all ordered triples on that plane? We need X because this thing runs in the X direction. So X is going to be 1. And then we could choose Y or Z. We've got the relationship of Y and Z. So we'll just choose Y. So then we got X, Y, Z is 1 minus Y, according to that plane. So then you're going to use those to rewrite F for all 5 surfaces, and then you're going to do F dot N, and then you need to get your bounds. Oh no. It doesn't work with the thing. Yeah, that's really sad. It's on the video though. Is this what we were doing? Okay, so is there any one of those that you want me to write the integral for? Any one of those 6? The last one. All the others are 0? Okay, so the left, the back, and the bottom all turn out to be 0. Is that right? Okay, good. All right, that's good to know. So we already got the front. So let's do the last one. S6 was it? Again, S5. And so what did we say? We said X and Y, and we said X, Y, 1 minus Y. And what did we say? N was
0, 2, 2.
Thank you. Good. And then we're going to do the double integral of this, xy. xy is 0, is that right? No. xy is xy. Okay. Looking at the wrong thing. Y squared is y squared. Z is 1 minus y dot this thing. And then it could be dx dy. And then what will our limits of integration be?
0, 1, 0, 1.
So it's the projection of that into this plane, right? So it's going to be 0 to 1, 0 to 1. It's just a rectangle. So we got xy times 0 goes away. So radical 2. Question, Charlie?
So with the balance, are we still like thinking of it as the projection of the surface onto xy?
Whatever your u and v plane is. Yeah, so whatever your uv plane is, in this case the xy plane, you take that surface, project it in the xy plane, and that will be your projected region that will determine the bounds, just like we did before.
Okay.
Just like when we...
It was like xz, then we would look on the xz plane.
What's that?
If it was like x and dx dz, then we'd be looking at the xz.
If you do dx dz, you're going to take whatever surface you're doing and project it into the xz plane, and that will be then determine your bounds for that double integral. That's right. Does this agree with what you guys got? So it'd be that plus
S1.
S1, which again was, we did what?
0, 0, 1 minus 0, 1, y, dz.
Anyone do the math for either of these?
You get 7/3 on the S1, and then
Anyone else get 7/3?
You get 1/6.
Overruled, sorry. Anyone could do that?
Yeah, I got 5 squared and 2 over 12.
It's a good number. I like the ring to it. Is it right? 5 squared. You got that too, Mark? But it's the same. So that means you got, okay. So what's the conclusion then? What's the conclusion about the flux with this surface? It's going to be positive, meaning what? Net flow through the whole thing, and the net result, or the kind of the accumulation of all flow for the whole thing is going to be outward. Even though in some, it doesn't look like on any surface will be in. So we just have outward in the front and on the diagonal plane, and zero through the others. So then it's positive flux. Questions on this one? Yes, please.
Why did we do dx dy again?
Because we wrote this plane in terms of x and y. So when S5, we wrote it in terms of x and y. So that's going to be how our integral is going to be x and y as well.
I mean, as opposed to dy dx. Doesn't matter.
Because it's just a rectangle, 0, 1, 0, 1. So it's just your type 1 versus type 2.
Yeah.
You could do dy dx, but you just got to make sure that you have your bounds right. But because it's just a rectangular with all constant limits, it's just free to switch. But if it wasn't, if it's like this one, right? If you do dz dy, you're going to have to make sure these are adjusted correctly. You have to change those. And it just goes back to all this. You're using everything you did for double integrals. Nothing's different. Make the picture, get the bounds right. Other questions on this one? Okay. There's another one. Find the flux through S. The closed surface is the part of the cone. Z equals x squared plus y squared. Below z equals 4. And the horizontal disk at z equals 4. So this is like, an ice cream cone that you got jipped, right? You just only get filled up to the top of the cone. You don't get the nice round scoop at the top. And then your vector field is y negative x z, and we're going to orient outward. So what do you predict for this problem to make it the easiest? What's going to be the approach we're going to use on this one? Yeah, cylindrical coordinates or polar coordinates, right? Cylindrical coordinates. This now, you've got the cone, sorry, z squared. Sorry. Is that what I want? Sure. Or square root, yeah. It's just okay, thank you. That's the cone.
The cone is no bar. The radius is this changes here too because the disk is not just a circle. Yeah, so it's a disk that's only got one part where it's going out. So if you did x, you would want to change it to a disk. You don't have your on values 4 because it's a circle all the way around. You have all points. This is 4. This is 4. This is 4. This is 4. So yeah, so then you have to have a lot. Yeah. Otherwise, if you just circle, yeah, you just go. Yeah. Chris, when you compare this with the S2, so arc is something that's the R sine theta, and then R
No, you don't.
This fits the thing that we had.
Oh, what the heck? Just do that. Makes it a lot easier.
Oh,
So, yeah.
I'm not sure.
So how did you parameterize that surface then?
The cone?
Yeah.
Just with R and theta, or cosine theta, or sine theta, and R.
Oh, okay.
Okay, so then we find the magnitude. That's fun. That's always fun things.
For the cone. X, Y, and Z. Yeah, it'd probably be better to use that generic form. A lot simpler than trying to do it the other way.
No.
No?
So is it D?
No, that wouldn't work for this because that's
Just keep working.
Yeah.
Oh, for the cone.
Well, yeah, because this is generic form, so X is not circular.
Yeah, that's
So you have to rewrite
because
that.
that's F n. I just this is at I just calculated the cross product. I didn't divide by the magnitude. What does R change from so there? You're right.
I'm sure if we rewrote it for we could find a
I
cone.
don't know if there's some connection here though. Or some.
You might be able to change it, but you would have to,
This would zero the surface.
because your X, Y would have to change the R, the T, R, and Z, and you would have to, I can't remember all the steps, but I'm pretty sure you can transform it.
Just keep working.
So how did you get your normal for S2?
For S2,
You have to
the flat disk.
No, we call
The
it
cone.
I call it flat disk S1.
Okay,
Or
so
S1.
for this
I'll
one,
just change it.
I did negative 1 over root 2 cosine theta and negative 1 over root 2 sine theta and 1 over root 2.
How did you write that? Oh, you took.
The partial derivatives.
Okay, so yeah, that gives the cross product. Okay, so
Have an R in there?
And then the magnitude.
We never changed it to polar. Okay, are there any questions? How about let's look at S2 first. So parameterization in R and theta would be X, Y, and Z is always 4. So we need R and theta because we need all the points on that disk. So we need R to vary and we need theta to vary. But Z is always 4. Okay, then we got the easy orientation, the 0, 0, 1, outward, right, outward. And so then the question is, isn't it R, d theta? The answer is no, because we're not switching from rectangular to polar. We started in polar. And so for flux, it's just going to be du dv. And actually that R is kind of built into this dot product. When you do this dot product, f dot n, that kind of has it already in there. Okay? So if you're starting with R and theta as your u and v, you do not inject an R in there. It's when you're changing from rectangular to polar that you include the R. So questions on S2. All right, then I got started on S1, and now here we're going to need to do the cross product. Why? Because we've got vectors in all directions coming out of this cone, right? We can't just call an n a constant. So I did r sub r cross r theta, and I got this cross product. Negative r cosine, negative r sine, and r. So the question is that outward orientation of these n vectors? Yes or no? How can you tell? Because we gotta have outward orientation. Maybe it was maybe we should have done r theta cross r. Who knows? That's kind of a weird thing to try to understand what's going to give us outward, right? So I could have done r theta cross r, and I would have gotten everything the opposite. So which one is the outward orientation according to this surface? How can we look at that and see if it's outward or inward? Yeah?
Just the way the R points, I guess.
Okay, so tell me.
It's inward.
This is inward because?
Because the R is positive.
And r is representing what here? Z. So if r equals z, what are values of r? Always positive. And so that means z is positive, meaning this is the, which orientation? Inward. You see, this is the inward orientation because this is giving us positive z values, which would be ones going in. So all we have to do to fix it to get the inward is, or outward, just take the opposite of the whole thing, right? Just the opposite of n. There's our outward orientation of the cone. So I should have done r theta cross r to get outward orientation. Who would have known that? You know, because this is like, what's the right-hand rule between r and theta? That's just like, you can't wrap your head around that, right? Well, maybe you can. Let's see. R, yeah, maybe like if you point your fingers away from the origin and sweep counterclockwise, that gives you positive z, I guess. Yeah, I guess it works. Okay. And that's not what we want. We want z to be down, so we want negative. Okay. So now we're ready to do it. This is then going to be our r cross r, so f is r sine theta, negative r cosine theta, z dot the normal, which is r cosine theta, r sine theta, negative r, and that's going to be theta. R goes from, it's going to be the same disk as this. It's going to be this exact same, because that projection of that cone is the exact same projection as the disk, so you're going to get the same limits. So we're going to have r cosine, those cancel. So do we get negative r squared? I thought it was going to turn out to be 0. All the flux is 0, but I guess not. So this will be r cubed over 3, 64 thirds times 2 pi. This will be something. Okay, any questions on setting those up? So what we do, we'll add those together. To get the total flux outward for this closed surface. Ask me. There's so much going on here. So if you have a question, don't hesitate to ask. Yeah.
For the S1 initial R, so S1 R and R theta, R and R theta.
Huh?
How do you? So do you just replace X, Y, Z with just the?
So we know x's are this is still, when we parameterize these surfaces, we're still doing an x component, a y component, and z. Okay. No matter what two parameters we pick, because we're working in R3. So this is x, that's our standard x, right?
Yeah.
That's our y, and then where does z come from?
Okay, so
the cone, right? So we're going to do square root of that squared plus that squared, which turns out to be r. So that's our z. So this comes from that.
Yeah.
Yeah. Other questions? So you're always doing f dot n, but is n variable or is it constant? If it's constant, don't do the cross product. Just figure out what it is, and it's the same for all points on your surface. But if it changes, then that's what the cross product is. The cross product is giving us the n for any ordered pair on the surface, which is changing. So it's a function, right? So here, n is a function, according to r cross this. And here, when we do n's, it's because it's the same for the whole surface. It's a plane. It's a planar surface, so we can just figure out what n is and keep it the same for all of them.
All right, thank you. That makes sense.
Okay, so, yeah, please.
How does the inward and outward orientation?
For the cone? So I did r cross, I did r sub r cross r sub theta. I could have done r theta cross r sub r. So I looked at the result, and I wanted to see that whether that's outward or inward. So r is always positive. That means z is always positive. That means those vectors are positive. So positive vectors on the surface of the cone, those point in, they have a positive z component. Those both point in or out. So in is going to point like this, and out is going to point like that. So we need the outward orientation. All those z components are going to be what? Positive or negative? Negative. The way it turned out, all these are positive because r is always positive. So I flipped it. Better? Okay. Do your homework.
Is it just